Okay, this is day 2 of the level chemistry notes. So let's get started. What we want to do today, we're going to describe the historic development of the atom and the periodic table. And we're going to talk about protons, neutrons, and electrons in atoms, something that you guys probably already know because it hasn't been all that long ago since you learned these things. So I think you guys will recognize a lot of it. Okay, so the smallest particle of an element that has the properties of that element is called an atom. In the slide you see we have iron nails, iron atoms, and a single atom of iron. An absolute smallest piece of iron that there could be is one tiny atom of iron. Okay, not an iron nail, that's made up of millions and millions and millions of iron atoms. But the smallest particle, the absolute smallest piece of any element, is called an atom of whatever element that is. In this case, we've got iron. Different subatomic particles that you probably remember, it's just been a while. We have protons, neutrons, and electrons. Protons are positive, neutrons are neutral, and electrons have a negative charge. Again, the smallest particle of an element that has the properties of that element is called an atom. And here we've got different pictures of how a water molecule is put together. The first has how it's put together as a solid in ice. These are water molecules. As a liquid, they're able to move past one another. And as a gas, water molecules move really, really fast, and they're in constant motion. As you start to zoom in on water, at what point does oxygen, the oxygen part of water, stop being an atom? Okay, so here in the first picture, you have water, just a glass of water. Okay, then you break it down. Well, water is made up of 2 hydrogens and an oxygen. When you break apart the 2 hydrogens from the oxygen, you have the single hydrogen atom, and an oxygen atom. Well, still at this point, oxygen's still an atom. But once you break down oxygen, what's oxygen actually made of? An atom of oxygen is made up of protons, neutrons, and electrons. And those protons, neutrons, and electrons are generic types of particles. They can be put together in a lot of different ways to make a lot of different elements. Okay, so at the point that oxygen is broken down into its protons, neutrons, and electrons, that is when oxygen stops being oxygen and just starts being protons, neutrons, and electrons. Okay, a little bit of history. Around 450 BC, the Greeks proposed that all things are made of the 4 basic elements: earth, wind, fire, and water. And how do you think that they came up with those? Okay, they didn't have microscopes, anything like that. Those were things that were visible to them. Those were the known things. So they thought that that's what all matter had to be made up of. 2 philosophers, 460 BC, Democritus is the first person to theorize about an atom. Now keep in mind, this is absolutely fascinating to me that Democritus was able to even think about the atom and think about the nothingness of space, and that matter's got to be made up of something smaller that we can't see. He lived in a robe, in sandals. He didn't have indoor plumbing. Okay, he had a dirt floor. And Democritus was so ahead of his time, being able to come up with this idea of an atom. He said that atoms, matter's composed of empty space through which atoms move. So later on, you've probably heard of Aristotle. So later, Aristotle kind of debunked Democritus's theory of the atom, which was actually correct. Aristotle was a politician, and he criticized Democritus. He said that there's no such thing as the nothingness of space. That doesn't exist. And since Aristotle was a little more popular at the time, nobody believed Democritus. They kind of just put his theory on the back burner until later, John Dalton, much, much later. John Dalton started theorizing about matter and atoms. He said that all matter is made of tiny spheres that are able to bounce around with perfect elasticity, and Dalton called these things atoms. And he actually took that from Democritus's term atom. Dalton is called the father of the atomic theory because he's the first person to start, in a modern way, start theorizing about the atom and make assumptions about atoms and things that he couldn't see. His atomic theory, now you're going to need to know all 4 parts of his atomic theory. Dalton said that all elements are composed of tiny indivisible particles, and he called them atoms. They're indivisible. Also, Part number 2, atoms of the same element are identical and that each element is unique. Okay, atoms of the same element. So he theorized that every hydrogen atom is identical to every other hydrogen atom. And we're going to talk about why number 1 and 2 aren't quite correct. Number 3, atoms of different elements can physically mix or chemically combine to form compounds. 100% correct. Absolutely true. And then part 4, chemical reactions occur when atoms are separated, joined, or rearranged. Well, at the bottom, you see much of this theory is still accepted. Some changes have been made to numbers 1 and 2. So number 1, all elements are composed of tiny indivisible parts called atoms. Atoms aren't necessarily indivisible. They can be divided into their protons, neutrons, and electrons. At the point when Dalton came up with his atomic theory, he didn't know that. Okay, so that's why this one's, there's a little bit of a change to number 1. Number 2, atoms of the same element are identical. Okay, they're not identical. They're really close, but they're not identical. An atom of carbon can have 3 different forms. It can act the same, bond the same, react the same, but it would have a very slightly different mass. These are called isotopes. Almost every element has isotopes. That means an isotope is an atom that has just simply a different number of neutrons and it weighs a little bit different, but it looks and acts in every other way exactly like all the other carbon atoms. Think of triplets. Okay, somebody has triplets. You have triplet girls. Okay, those triplet girls are going to look identical triplets. They'll look identical. Everything looks the same on them, but it's not normal for every triplet to every time, all the time, weigh exactly the same. They might be off by just a few ounces, but those triplets will have that teeny weeny weight difference. Okay, so that's how you kind of can think of the elements are identical, but not really. Their masses can be a little bit different. Okay, another scientist, Eugene Goldstein, discovered positive particles in atoms. Later, Rutherford called these protons, and I think you know what protons are. They're the positively charged particles inside the nucleus of an atom. J.J. Thomson passed electric current through a glass filled with gas. He discovered that the beam of negative charges traveled from the cathode to the anode. So that's lots of words for his discovery of the electron. Okay, he used, it was a cathode ray tube experiment. It's a very famous experiment, but in this experiment, he discovered negative particles, and he called these negative particles electrons. This is what the model of an atom looked like in J.J. Thomson's head. He called the model of his model of the atom the plum pudding model. So in his plum pudding model, it looked like either that picture of plum pudding or a chocolate chip cookie, but what he thought of an atom to look like is a big blob of positively charged material and electrons just floating wherever they want to. All over the place, just running all over the place inside that atom. Okay, that's his vision of what an atom was. Ernest Rutherford was actually going to try to prove Thomson's plum pudding model correct. He thought that J.J. Thomson was correct, so he did this gold foil experiment to try to prove Thomson correct. He actually ended up proving Thomson wrong. Okay, he fired helium nuclei at a piece of gold foil. So you see there in the picture, that's a piece of just like aluminum foil, but it's gold. It's been hammered into a really super thin, tiny, tiny, tiny sheet. When these positive particles were shot through the gold foil, they hit a screen that surrounded the gold foil, and every time that positive particle hit that screen, it would light up. There would be a little photon of light, a little piece of light. And what happened was all those alpha particles were going through the gold foil and hitting the back of the screen, which is what he thought. Well, every once in a while, one would bounce back at him. Instead of going all the way through the gold foil, it bounced back. It's like it hit something and bounced back, like if you were playing wall ball. You hit the ball and it bounces back. Well, this is not what he expected to happen. So he found that most of these passed through the gold foil, but about 1 in 10,000 were deflected back at him. So what happened is he disproved Thomson's model. what he discovered was the nucleus of the atom. So what those alpha particles were hitting and bouncing back at him, they were hitting the nucleus, which is a very tiny, 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 dense, positive core inside the atom. And when that positive particle hit that core, it bounced right back. Okay, so he discovered the nucleus. All right, he wasn't intending to, but he discovered the nucleus. Rutherford overturned the plum pudding model by accident, but he did. He concluded that atoms are mostly empty space. This is a big one. We don't think of them as being empty space, but the nucleus is so, so, so tiny compared to the rest of the atom that most of what's making up that atom, whether those electrons are running around, empty space. Also, atoms have a solid nucleus at the center, which contains most of the mass of the atom. Why? Because protons and neutrons live in the nucleus of the atom, and those are the only two things that have any real mass. And three, he also discovered or concluded that this was the first time that atoms were thought to have a nucleus. Prior to this, remember the plum pudding model, there was no nucleus. It was just a big blob of positive matter with electrons spread throughout it. Well, that's not the way his model was. His model had this nucleus at the center. And this is the first time that someone actually had talked about there being a nucleus of an atom. Niels Bohr, another scientist, he believed that electrons were in orbits like planets orbiting the sun. And this is a good one for us we can visualize that. We can see, we know what the planets look like orbiting the sun. Well, this is the way Niels Bohr thought that electrons orbited the nucleus. He believed that each orbit is able to contain only a set number of electrons. And he said that each orbital had a very fixed energy level, fixed amount of energy through which those electrons would travel. James Chadwick, another scientist, he discovered the neutron, which is very important because it's just as much mass. It weighs about the same as a proton. So a proton's mass is equal to a neutron's mass. He discovered this neutral subatomic particle that kind of held everything together. It holds those protons together because they're positively charged. Okay, they're wanting to push away. If you've got two positive charges close to one another, they're wanting to push away. Well, the neutrons kind of keep everything stuck there in that nucleus. It keeps them held tightly together. So for our atomic structure, the different particles that you need to know are protons, neutrons, and electrons. Protons will have a positive charge, and they have an approximate mass of 1 atomic mass unit. AMU stands for atomic mass unit. Neutrons are neutral. That means they don't have a charge. They're not positive, they're not negative, they're neutral. And their mass is approximately 1 atomic mass unit also. Electrons have a negative charge, and they're so, so tiny we don't even count them. They're super, super tiny. You can see that they're, 5/10,000ths of an atomic mass unit. They're really, really small. Okay, think of electrons as earrings, okay? Electrons are like earrings, tiny mass outside the nucleus. If you take them off, your mass doesn't change enough for the scale to even notice it. So if I go step on my bathroom scale and I take my earrings off, nothing's going to change, okay? That's what electrons are like. That's how small they are and how little they affect the mass of an atom. The nucleus is a tiny positive core in the atom, and it contains most of the mass of the atom. Protons are positive, so the proton is the positively charged particle found in the nucleus of the atom. Neutrons are neutral. Protons positive. Proton and positive both start with P. Neutrons are neutral. They both sound alike. Neutrons are neutral, and it's the particle with no charge found in the center of the atom. The letters P and N are close to each other in the alphabet, so they're also close together in the nucleus. Okay, electrons, E is way away from P and N, but P and N are real close together in the alphabet. So those are the two things that are stuck together in the nucleus, the protons and the neutrons. And also remember, neutrons are not negative. Neutrons are neutral, NEU. The electron's the negatively charged particle found outside the nucleus, and it is responsible for everything, we'll come to learn. Okay, it's very tiny, but it is super important. The atomic number. So this is a box off the periodic table. The atomic number is a whole number, and it's going to be at the top, and that tells you the number of protons in an atom. It identifies the element. Every element has a different number of protons, and it's very unique to that atom. So Anything that has 2 protons has to be helium. Anything that has 1 proton has to be hydrogen. Okay, and so on and so on. At the bottom of the box on the periodic table for helium here, you see the average atomic mass. 4.003 is the average atomic mass for helium, and each average atomic mass is different, and it's an average because it's an average of the isotopes. Remember I told you that the isotopes earlier, I told you isotopes had slightly different masses. Well, when you average those together, you get the average atomic mass that's at the bottom of the periodic table, or the box on the periodic table. So in a neutral atom, so neutral means no charge. In a neutral atom, electrons will equal the number of protons. Okay, think about it. If electrons are negative and protons are positive, if I have the same number of protons and the same number of electrons, they cancel each other out. So the atom is neutral. The mass number is the average atomic mass rounded to the nearest whole number. So what do you think the mass number for helium would be here? If it's 4.003, 4.003 is the average mass. I need to round that to the nearest whole number. What do you think that is? It's 4. 4 would be the mass number for helium. So helium has how many protons? And how many electrons? 2 and 2. The average atomic mass for helium is 4.003. It's at the bottom of the box on its periodic table. And the mass number for helium is 4. In a neutral atom, you may have learned APE-Man. I love APE-Man because it's so helpful. APE is atomic number equals protons equals electrons. Okay, so what that means is the atomic number that you see on the periodic table is equal to the number of protons. And in a neutral atom, protons equal electrons. Okay, APE. Man is the mass number, which is that rounded number, mass number, minus atomic number. That gives me the neutrons. So I can find protons, I can find electrons, I can find neutrons just by that box on the periodic table. So let's remember APE-Man and think about what we have here. K is the symbol for potassium. What do you think its atomic number is? Right, it's 19. So if it has an atomic number of 19 and atomic number equals protons, how many protons? 19. Okay, and protons equal electrons, 19 electrons. Good. And then, popped in too fast. The mass number, remember the mass number is the rounded number. So the mass number here, 39.098, rounded to the nearest whole number is just 39. 39 minus the atomic number of 19 gives me 20 neutrons. So I've got protons, electrons, and neutrons I can find. Okay, so how many protons do you think there are? Okay, and how many electrons? I'm going to pop it in, but I want you to think for a second. See if you can work through it. And remember, neutrons is mass minus atomic number. So you have to do the rounded mass minus the atomic number to get neutrons. So what do you think? There's the protons, there's the electrons, and 4 minus 2 gives you the neutrons. Okay, how about carbon? 6 protons, 6 electrons, and 12 minus 6, 6 neutrons. How about silver? Ag is silver. How many protons? 47. Protons equal electrons, so 47 electrons. Neutrons, we have to do the mass number, which is that rounded number, minus the atomic number. So in this case, it's going to 107.868 rounds to what? It would round to 108. So you have to take 108 minus the atomic number 47, and that gives you the number of neutrons. Okay, lithium, a little bit easier, smaller numbers. How many protons? How many electrons? And what would be that mass number? What would you use? 6.941 rounds to what? Rounds to 7. Okay, lead, Pb, lead. 82 protons, 82 electrons, and 207 would be that number rounded. Minus 82 is 125. Argon, we're through argon. All right, so this is a little bit trickier. You have to have your periodic table handy. So what do you think the atomic symbol Al stands for? Look on your periodic table, see if you can find it. Al stands for aluminum. And if you look for atomic number 13, you'll see that's where aluminum is. And we've given you the average atomic mass for aluminum, which is 26.982. So from this information, you should be able to figure out protons and electrons. Remember that atomic number is equal to the protons and electrons. So there should be 13 protons, 13 electrons. How about the neutrons? You have to round that average atomic mass and subtract the atomic number. So that would be 27 minus 13, 14 neutrons. Okay, this is all of it filled in. I really hope you worked through it. It would really make me happy if you'd work through it. But make sure, check our work. We make mistakes. We're not perfect. So that's the end of our slides for today. Do your homework. Do your attendance check. We'll see you really soon, and we really do miss you.